Hey guys, as you know, when you're finding maximums and minimum points for a given model or for a given function, the process for finding both the max and the min, it's the same. You take the first derivative, you make it equal to 0, and then you find the critical points, which are the possible candidates for maxes and mins. Now, given that the process is the same for finding maxes and mins, we need to find a way, we need to use a strategy, a test to test whether we found a max or a min, and that's where the first derivative test and the second derivative test, they come into play. What we're going to do in this exercise right here is to use the second derivative test to test whether the maximum that we got, well, it's actually a maximum. So in a nutshell, we're going through an optimization problem, one that involves a box, and towards the end, making sure that we know how to apply the second derivative test. So let's get to it. And by the way, you can find the exercise list on optimization problems in the description of this video. Pedro wants to construct an open top box with a square base, meaning that the base is a square, these sides are the same, and there's no lid. The total external surface area of the box, meaning the four sides plus the base, it is equal to 108 centimeters squared. Let x represent the side length of the square base in centimeters. Therefore, we have this and this both equal to x, and x is in centimeters. We also have the height h, which is right here. And we know, again, it's important to restate this fact. The total external surface, meaning the base plus the four sides, they have an area of 108 centimeters squared. If you go through the cheat sheet on optimization problems, you're going to realize that you already have a bunch of information. Number one, we do know what is happening in this exercise. We have a fixed amount of material, meaning the surface area of the box, which, by the way, was given 108 centimeters squared. We do know that the base is a square. At some point, we're going to find the dimensions of the box, so we maximize its volume. So at some point, we're going to maximize the volume. And the restriction, which is the finite amount of something, well, the restriction is the surface area of the box. We know that S, representing S as the surface area of the box, is 108 centimeters squared. We also have the sketch. So item 2 is done. We do have variables attributed to the given quantities. We can call the only variable that we didn't choose is volume. We can choose capital V for representing the volume. And right now we're going to work with the restriction. We know that the surface area is 108. Therefore, the area of the base, which is x times x, plus 4 times the area of the side, we have 4 sides, x times h. This is 108. Which allows us to write for hx equal to 108 minus x squared. Therefore, h can be substituted later by 108 minus x squared over 4x. We can also break this fraction into 2, which gives us 27 over x minus x over 4, which is exactly what the exercise A, asked us to do, which is to prove that h can be represented as 27 over x minus x over 4. So question A is done. And now let's tackle question B. So what is the volume of this box? Having no lid obviously does not change the volume. The volume is still area of the base times the height, which means V is equal to x squared times the height. Now V as a function of x only does require us to substitute h, which was found previously, into V, which gives us x squared times 27 over x minus x over 4 in bracket. Therefore, by foiling, we can rewrite v of x as 27x minus x cubed over 4. So we already defined the function that we need to optimize, and the function is written in terms of one variable only, which is exactly what we need. Now, finding the critical points is the next step of the process, which will lead us to actually finding the maximum possible volume. Now we're going to go back to our function v of x. We're going to differentiate it and set it equal to 0. And this is not the hardest derivative. We have v prime of x equal to 27, which is the derivative of 27x minus 3x squared over 4. And setting this equal to 0 gives us 27 equal to 3x squared over 4, 108 equal to 3x squared equal to 36, therefore x equals 6. 6 centimeters, it has to be a positive number. That's why we can, in this case, ignore the -6 as a possible solution. So x is equal to positive 6 centimeters. It's important to remember that this is the critical point, which is a number in the domain of v of x. In this case, the function that we have is v of x, such that either the derivative is equal to 0, which in practical terms is what we want, or the derivative does not exist, which is not something that we need to worry about. So for this case, we're dealing with points where the derivative is equal to 0. These are going to be the candidates for maxes and mins. All right, so right now we're going to use the second derivative of v in order to prove that we actually got a max. And it makes a lot of sense to use the second derivative in this question because, well, differentiating v again, it's quite easy. If v prime is 27 minus 3x to the fourth, x squared over 4, that means that v prime prime, meaning the second derivative of v, is equal to 0, which is the derivative of 27, minus 3 over 4 times the derivative of x squared, which is 2x. Therefore, v prime prime of x is negative 3x over 2. And how does the second derivative test work? We are going to take our critical point, which is x equals 6. There are two critical points for this function, as I mentioned before, -6 and 6. But 6 is the only one that matters for this context. We're going to take it and replace it into x for the second derivative, or on the second derivative. And by doing so, we get v prime prime of 6 equal to -9. And the only thing that matters here is that this is a negative number. If we have c as a critical point and the second derivative at c is less than 0, meaning it is negative, then f has a local maximum at c, which in this context means that the volume is a max when x is equal to 6. So therefore, x equals 6 gives us a maximum volume. And the exercise might ask you as well, what is that volume? And what we need to do to answer that question is to find v of 6, not v prime of 6, not v prime prime of 6, but v of 6, which is 27 times 6 minus 216 over 4. And coincidentally, this is also equal to 108, but this is a volume, so 108 centimeters cubed. It's just a coincidence that the numeric value was the same as the surface area. Another question that might be asked is, what are the dimensions of the box? Which means that we need to find, in that case, h when x is equal to 6. So we have 27 over 6 minus 6 over 4, which is 3 centimeters. And that is it. That is how we use the second derivative test in order to prove that we actually got a max.